So it's a pleasure for us actually to be a part of this X Lab and to give you a tour of this. We have Professor Frano with us, and I'd like Professor Frano to say some welcoming words to everyone.
Sounds great. First and foremost, thank you to SPS, to Jillian, to Zach, to Danny, to Aisha, and others whom I may not have mentioned for organizing this. I think it's extremely important for undergrad students to see what research looks like. And normally you'd be able to go to the lab, but this is the best we can do now, and we're doing it for happily, and look forward to the day when you can visit the lab in person. I'm outside right now. I just came from the dentist. Turns out I had to get some X-rays done on my jaw, and I found it fitting that you'll hear about X-rays today on the same day that I just got a healthy dose of X-rays on my face. So first lesson is be careful with X-rays. Don't get too many of them on you. But when you need to, you need to. So that's what I just did right now. So I'm sorry I'm not there, meaning, well, I'm here. I don't know. And secondly, and most importantly, I want to also thank Dong and Rhoda, my students, for helping with this presentation, this tour. And I really hope you enjoy it. And again, I look forward to seeing you in the lab one day when we go back to normal. So thanks again, everyone, and hope you like it.
Thank you, Professor.
Thank you, Professor.
All right, so welcome to X Lab, and I'm starting the tour. If you have any comments, the organizers, else I'll just start with it.
By all means.
Okay, thank you. So the outline is, the way we are going to do this is we will have an introduction of what strong interaction is. The strong interaction physics is what we do. So what we exactly do is the details is in the second part. How we do it is the third part, and fourth part is the Q&A. So first thing is the length scale. And please feel free to stop me during this presentation, or by Dong, and when she comes in, we are happy to take your questions and as much as we know. So the first thing is that the length scale that we are interested in. So this is the right hand side. You see the length scale of interest with marked by a dashed line, which is falls in the atomic and micro region. So 10 to the power minus 1 nanometer to 10 to the power 7 nanometer roughly, which is the biggest sample size that we roughly always have. So everything quantum kind of happens from 10 to the power 1 nanometer to 10 to the power 1 nanometer. Classical things starts to happen from 10 to the power 2 nanometer and onwards, which is also pointed here. So now there are two different things of interest we have. One is complex materials, where atoms and molecules are clumped together. There are too many of them, and they concoct and they conspire to do fantastic things in hard condensed matter. And also these features are also important in developing biochemistry and interaction in the macromolecular biology side. But that is also like soft matter. So hard matter and soft matter and complexity in the regime of strong interaction is where we love to wiggle our brain. Now, in members we study in quantum and classical regime in quantum regime we study electrons, photons, and ions. Unlike high energy physics, we only have these three things. So now on a right-hand panel, you have the depiction of an electron, which is not like a solid sphere, which is a probability distribution, as some of you have already encountered that in your class. And so there is a probability of an electron to be perceived by a detector at a location. It's not exactly one at a single position, but it follows some distribution of it. But when it is bound, when it is free, it looks like exactly like a plane wave. So both of them are actually electron, depending on how much photon it has eaten. So an electron eats photons, so that's electrons and photons are members, and ions are the one who binds them, takes photons from them. And classical, the same thing happens with polymers. So there's like interacting polymers. They are like long length chains, and Dong is an expert on this. She knows a lot of details about that, and she'll tell you down the line. And that there is like, we will have nanocubes and polymers where this interaction, we develop some strong interaction and study them. So these are the members that we study. Now, what happens when you have the ions in it? So I'm going to talk a bit more about the quantum because the regime that I'm working on. So the quantum regime is that when you have an electron like that, when you have an ion, so the blue things are the electrons and the red things are the ions, and they trade in electrons. They don't trade in the energies.
Hey, what's up, guys?
Hey, Lester.
Hey, we were doing a tour earlier. I'm looking for a notebook.
Please feel free to find it. There is a few books. Sorry about that. But by the way, Lester was here, and Lester is like the god here. He does like maintains the lab such a well way so that we can do amazing sciences. So back to the thing. So we have members, that's electrons and photons. So electrons eat photons and becomes in a different, looks different. Whereas ions are the one who trade in electrons. They don't trade in energies. It's like big corporation. They trade in humans. They don't trade in money. So, and then that's how the ions. So electrons are coming from an electron, from an ion to another. That's what you call it, the mobility. And so on. So, and you create a ton of ions like that, and you have a system, and the system follows an interaction regime. Like it follows some physics, the rules of physics that we set. We want to grow it like that, and that happens. So yeah, the interaction happens a bit. There is basic two interaction that we involve in, a love-hate kind of interaction. And I would ask John to tell some more about the classical interactions here.
So, if you guys can see on the figure, like on the right-hand side, is this a kind of like a soft condensed matter system, where we're looking at like on the picture on the top here, is this like a thin film of polymer. And this string here, you guys see here is silver nanocube. And upon, like when you have like a thin film of polymer, we put sprinkle silver nanocube on top, and then we heat them up. And these silver nanocube kind of like self-assembling together to form one-dimensional string. And this is what's like we are like currently interested right now. We want to like figure out like what is exactly those interaction is, like how these polymer interact together to form like one-dimensional string. And that's what we currently doing.
Yeah, so these are the love-hate relationship in quantum system, where the electrons are mediated by ions, and like they love or hate each other between them. So we know that electrons don't like another electron, but through ions they start to like each other, and sometimes they form pairs. And so this is the interaction, basically interaction between strong particles. Like in classical regime, the nanocubes, they don't like each other, or sometimes they like each other depending on the polymers, through which their interaction is mediated. The physics is basically what we know, right? The basically is electromagnetism. So two electrons, they interact with electromagnetism. It has been known, the quantum mechanics, one particle quantum mechanics we all study two-particle quantum mechanics is quantum field theory that we also study in like space and time regime. In classical mechanics, it's like classical mechanics, one particle, two particle is maybe many particles, is like classical field theory, two particle interactions. But what happens when we have 10 to the power 23 of them? It's not trivial to go from one to another, because as you can see on the like the presentation here, there is like two electrons coming together. They all have their own distribution, but when they are coming close together, the distribution is changing in a non-trivial way. And it's like weird at one point, and then it changes a bit more. And the projection is shown on the top in the blue. And it becomes difficult to analyze this kind of behavior when there is 10 to the power 23 or Avogadro number of them. To give you an example of what a strong interaction is, I have this triangle down below. So triangle, on the left side of the triangle, there are 3 points on top. And these are the 3 balls. The balls can take one of the colors, white or black. Now, when the rule of the land is that they will take the color of their neighboring ball, they're happy. They take either white or they take either black, and they become exactly like their neighbors. But when the rule of the land is you have to become exactly opposite to your neighbor, then two of the neighbors know what to do, but the third neighbor is under, I don't know, it's indifferent to their choices, or they're too much influenced by their choices and doesn't know what to do. This is kind of a regime of strong interaction. And imagine this kind of scenario with 10 to the power 23 of them. Like, it's a huge, 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 huge number. There's a very nice article I would ask every one of you to read that gives the glimpse of the physics that we study. That's called More is Different. It's by Philip Anderson. I believe it was given as a colloquium talk in UCSD back in 1970s or something. But it's an amazing talk, and it's available in Science. So what do we do? To study these systems, we grow a system where we can control this interaction. Like the rule of the land that I said for the 3-particle thing, we will say, what is the symmetry of this thing? What are the different states it can take? What is the topology of this place? Members of the land, the electron and photons are kind of the defined thing that we study, but the main ingredient in controlling the interaction are the ions. And there are external forces like how much strain we can give, how much pressure we can apply, what we can apply twists to them, doping, magnetic field, temperature, and all sorts of that. For soft condensed matter system, we are collaborating with others where we have these nanoparticles that exactly like Don explained. They are sprinkled on top of like polymer thin films, and they are different lengths. There are different grafting to the nanocubes, and there are different polymers that can enable or disable some interactions. And the interaction change varies with the grafting lengths, the nanocube sizes, temperatures, and all. But it's mostly done with the collaboration with nano engineering department. And so they're amazing people. So now we will go into the details of the pulse laser deposition system, and I'd like to Don take over from here.
So I'll take over from here.
And let me know where I should point if I have to.
Okay, maybe you can start. So like, so now we already like introduced you guys about like what type of like physics we are studying, and now you guys can have a question like how are we gonna prepare the sample in order to study the physics. So in our lab, we're using a machine called pulse laser deposition, or PLD. And I'll go over like the overview of the machine, the working principle of the machine, and then advantages and disadvantages of it. So the picture that you guys see on the screen here is like an actual picture of a PLD machine where we have a laser short inside the black box here. And now we have like a focus lens in order to like focus the beam. Focus is down into the vacuum chamber here. And inside the vacuum chamber is where we actually roll in thin film sample. And here's like a little gate here. I don't know if you guys can see, but this is where we put the sample in here, and then we put it here between the vacuum chamber and this guy. There's like a gate in order to like control the vacuum of the system. And after we put the sample here, I'm gonna use this black knob here in order to like push and like take it in and then put the sample inside the vacuum chamber here. And we use like here we have the control station where we control the laser beam, like the energy of the laser and the time where we can deposit the thin film. And I'll talk more into detail like what's going on inside the vacuum chamber in the next slide. But here's the overview of the machine that we're using in our lab. So first of all, PLD is a physical vapor deposition technique that we used. It's use high power pulse laser beam in order to roll thin film of different material. So this is the picture of like inside a vacuum chamber where we have like three main components, which is the heater on top of it, and then here we have the substrate. The substrate is like the substrate that where you want to like deposit the thin film sample on top of it. And because of the geometry of the substrate like this, so when we put the sample inside the PLD, you actually have to like put it upside down. And down here we have a target. The target is like the material of the same type that you want to like make the thin film out of. And the yellow arrow here is like the direction of like the deposition. So when you strike the laser beam on top of the target here, there's gonna be actually like a plume, the plasma plume on top of here, and then it's gonna deposit the sample to the substrate, and like the thin film is kept like rolling from there. A little bit more into detail of like the deposition process. So generally speaking, there are 5 different states during the deposition process. So step 1, like at the beginning, there's gonna be like absorption. When you shine the laser on top of the target here, there's gonna be like absorption of the laser beam by the target material. The laser, like during this process, the laser energy is gonna transfer as electronic excitation. Like the laser energy is gonna convert into like thermal energy, chemical energy, like mechanical energy. And that's linked to the second state, which is laser ablation of the target material and the formation of the plasma plume, which is the yellow thing here. So laser ablation is like you removing the material from the surface by like irradiating it with a laser beam. And next step is plasma dynamic, which is the evaporate of material is spread into like the chamber as the plasma plume. And plasma is like similar to gas, except it's like a charged gas that's containing like highly energetic species like electron, ion, atom, molecule, cluster, cluster, like all kind of stuff in here, like very dynamic in here. And next step is this guy, they like highly energetic species gonna deposit on top of the substrate here. It's gonna evaporate and deposit on top of the substrate, like that's how like the thin film is rolling. And state 4 is the nucleation in row of the required film with the same composition at the target. So that's basically the 5 different states how we roll the thin film sample. And in every single state here, they need to be like optimized carefully for the roll of high quality crystal material. Like some like control parameter that we can use to optimize the process is like the laser beam energy, the distance between the substrate and the target, the pressure, the pressure inside the chamber, etc., etc. Or even like the temperature of the heater as well. So one of the reason why we use this to roll our sample inside the lab is because this technique is really easy to roll like multi-component film of the design stoichiometric ratio, or we can even like roll multi-layer film as we want, and this can give a like uniform thin film. So as you can see the schematic picture here, or this is like the thin film the substrate. Between here is the interface. And normally for a PLD machine, the thickness of the thin film, you can go from like 10 nanometer up to 500 nanometer. And like besides like easy to roll, like multi-component thin film of like multi-layer film and uniform, for PLD, like almost like there's no restriction on the PLD target. So we can like prepare like a variety of thin film sample that we want. And it's like this process parameter is like super easy to control, like as I mentioned before, like deposition rate, like heater, temperature, pressure, target substrate distance. However, like this technique also have like some like disadvantage. For example, it's not feasible for large area deposition because normally the area for the PLD deposition, the diameter of the circle is around 4 centimeter. And therefore it's not suitable for large scale deposition. And for some material, like there are like target fragment like inside the plasma plume, and it's kind of like reduce the quality of the thin film. But like despite like all of like the disadvantages, there's a lot of advantages that we can use for PLD, so that's why like I love using it. And up to this point here, do you guys have any questions for the PLD? If not, Brewer can show you guys like the actual PLD machine. Brewer, are you showing it? The whole PLD machine.
I'm showing our PLD lab. So, Don, can you please stop sharing? I guess maybe then this will become the main screen. Okay. Okay. Is everyone being a? Yeah. Can you see it?
We can see your video.
Oh, I need to be able to hear you. Okay. Yeah. Sorry. Oh, John, can you please stop sharing?
I don't know where's the bar. Oh, yes, stop sharing. It's not sharing now. Yeah, you can share it. Yeah.
So this is our lab. This is one part of it. On the desks over there, we have the powders of the samples with which we measure it in the stoichiometric ratios in there, and then we create right now you can see one of the thin films that we are preparing to create. Like this is after the deposition. You remember the plume is hitting at a point. That's the thing. So by the way, we create the powders. After we create the powders, we mix them well, and we create a pellet with the hydraulic press, which is way over there. Like at the end of that, we have this hydraulic press, which is this guy. And inside that, we place the powder here inside a puck, and just use this handle to crank up the pressure. And once the pressure is high, it creates a pellet. And then we take that pellet, as Dong said, inside this PLD machine, which is right over here. And this guy is the laser, on which the coherent is written on. So coherent creates the laser pulses, and the things inside this glass box are the focusing optics. So it comes out from this chamber, bounces off the lenses, and that's the final focusing lens, which then focuses onto the opening of the PLD chamber. This computer is where the controls are, and then after focusing, it enters the PLD chamber, where inside maybe it's hard to see, but let me try. Okay, yeah, it's hard to see, but there are pucks on the bottom, and there are that is the area where the plume is gonna hit. And once the plume hits there, inside this PLD chamber, we have our thin films. And this pump is what creates the vacuum here. This is a krypton fluoride laser, KRF laser. So it needs krypton fluoride gas, which is unhealthy gas to inhale. So it's like totally inside a safety closure. And rest of the gases are like nitrogen and helium, and yeah, for the compressor. So if you have any questions, I'm gonna stop my, I'm gonna keep the video sharing on, but please ask the questions here. We are gonna hold on for a bit of time.
Those optics in the glass box, are those focusing X-ray lasers?
Good question. So this is UV laser here.
Oh, okay, it's UV.
So yeah, this is not X-ray. We are not yet on the X-ray regime here, because we want not all the, so X-rays are relevant at the length scale of angstrom. So where that is the length scale of 2 particle distances. But we are creating like chunks of the material. So we are creating using the reaction, stoichiometric reaction. We are pressing the, we are creating the pellets. Inside the pellets, it's almost the PrNiO3 material. Say, for example, we are creating PrNiO3 material, thin films of PrNiO3. So we have already created the material once we have done the solid state reaction. But we haven't placed them in the exact symmetry as we liked. So to create the symmetry, we have a substrate. Substrate dictates the symmetry and the interparticle distance. And once we fire the laser up on the pellet, the chunks of the material is gonna blow up and gonna land on the substrate. Exactly like how you light up a candle and hold a paper on top of it, and it deposits carbon on it. If you light up a candle, that happens, right? So it's exactly the same principle, that we are going to fire up some energy on the pellet. It shoot up the material, but the material is gonna land according to our defined rule. That's the whole point of PLD.
That's really cool. Thank you for clearing that up.
Any other questions? Okay, then if there is no other, I'll get back to the I'll stop sharing this video and get back to the next phase, which is the X-ray like characterization. Now we have grown the sample. What after that? So I'll go to that part of the story now. Oh, thank you. Okay. So next part is, what do we do to characterize this material? And that takes us to the story of reciprocal lattice space. So now how many like have you studied reciprocal lattice space in your classes. Okay, so let me tell a bit summary of it. It's exactly like how you define a direct lattice, which is, so in harder condensed matter, that what I have shown is that we define a rule of the land, right? How the symmetry of the land, how we want the atoms and particles to land exactly where we want. Now, what is the rule of the land? That rule of the land is how far we want each particle to land. Like, for example, on the left, you see the direct lattice, which is like a square lattice. So what is the rule of the land? That at b distance away on the right, you will always find a particle if you go horizontal. A distance away, you'll always find a particle from a particle if you go vertical. So we call this a square lattice, basically a rectangular lattice. But so, and also if you rotate the image by 180 degrees, it should look the same. Now, if A is equal to B, the rule of the land is if you rotate the image by 50 degrees, it will look the same. Sorry, 90 degrees, yes. Yeah. Yeah, if you rotate the image by 90 degrees, it will look the same. Now, reciprocal lattice is just defining the same thing, but in a different way. That's saying that, okay, what is the periodicity of this thing on that direction? So other than saying that it repeats after this n numbers of like after b length, we say what is the periodicity. So the and it's how to say, like if there is like, so if there is like 10 repetition on one side, there will be like, it's exactly like how wavelength and wave numbers are related, and to be honest, like in a direct comparison sense. I am sure you guys have studied wavelengths and wave numbers. So yeah, this is exactly, so k is 2 pi over lambda, right? So that's exactly how wavelength and wave number. So instead of saying what is the wavelength after which the repetition happens, I'm saying that within 2 pi there are that many repetitions. Okay, so same thing but different language. What's the advantage of using that language? So the first thing is that one is the Fourier transform of another. And Fourier transform is a beautiful thing in, wait, I'm not doing a good thing. What's the best way to have you guys be able to see? Okay, so Fourier transform is very important in system where there is translation symmetry. If you have translation symmetry, you want to know how the reverse relation looks like, because it becomes an easy problem. Things in real life are calculus. If you take a Fourier transform of this, that becomes algebra. So it's infinitely easier to tackle. It's infinitely more intuitive. It's infinitely more understandable in many other sense. So for example, how we take this Fourier transform, like on the left hand side, that's our real lattice, and I have shown here the real lattice in a whole different like in all different layers that there is. Now you can imagine that layers are extending on the right and on the left and on the bottom, but not on top. The top is an interface where the two arrows are our X-rays who are hitting the light, hitting the surface. Now, this is a specific situation that I have shown here, where the two arrows who are reflecting off of two different, like two next to each other surfaces, are constructively interfering. Now, when will that happen? When the path length difference between them will be an integer multiple of 2 pi, so that the wavelengths merge together exactly in phase, and they will create a constructive interference. And that's what basically how we take the Fourier transform of a material. So now, for example, this Fourier says what is the d spacing of these two planes, which is along the zero, say, y direction in this figure. Now, omega is how much I have rotated the sample with respect to you guys. Now, if I rotate the sample by 45 degrees, now you see I'm probing different layers altogether. Now the d spacing has changed. And all of this is related to lambda, which is the wavelength that I'm probing with, by 2d sine theta. So for every d there is inside the sample, I get a theta. So they are like one-to-one functions of each other. Right? And theta is the angle by which the incident ray, theta is the half of the angle by which the incident ray changes direction. So in other ways, it's if there was no sample, the incident ray would go direct like this. Instead, it is reflected by 2 theta. So this is called diffraction, and that is how we take Fourier transform. And if we map the whole thing in K-space, now I have included the instruments that we use to take the Fourier transform. So things in real space are x, y, z. Things in K-space are kx, ky, kz, where k are 2 pi over the lambda thing. So the k is the wave number. So if you have a plane wave, the wave of X-rays, you need 3 k values to explain it, right? Mathematically. And in the right hand side, what I'm showing how these k values are related to the reciprocal lattice. So A and B here, maybe I should have rotated it, but anyways, so yeah, you get the picture. So k values, k incident and k reflected, once they match this condition that they are on the surface of this circle, that's how we know that there is a diffraction. And one by one, rotating these 2 vectors, we scan this whole space and find where there are intensities and create this reciprocal lattice in that space. How we do it using an instrument? We use a 4-circle diffractometer. What's a 4-circle diffractometer? This is which has 4 circles in it. Now previously what we were doing is rotating the sample, right? So that is omega. Keeping this, so this is the omega thing. This is omega rotation, which rotates the sample. And there is 2 theta rotation, which is the detector, which finds where the scattered light went off. So how much 2 theta deflection it happened. Now real life things are not 2-dimensional, right? So I need another dimension to this, which is where this chi thing comes in. So x, y, z. So I get like all the 3 coordinates with omega, chi, and 2 theta. Why it's 4? This is a 3-circle, right? Why there is 4-circle, which is the phi. Phi is another argument we can use, but most of the time we don't. So it has like it has more intricacies, but it gives another degree of freedom that we don't care right now. But in a nutshell, this is how we take things from a real space to a reciprocal space. So real space ABC become reciprocal space HKL units. Now I'll take you guys to the other lab, which is our X-ray diffraction lab, but I have to walk there. So please bear with me. Yes, if you guys have questions, you can also ask me in chat.
So the goal of all this is to show you the three-dimensional lattice spacing in the X, the Y, and the Z directions. And that kind of tells you what kind of crystals your material forms. Is that correct?
Sorry, can you ask the question again?
Sure. So the goal is to use this diffraction to show you the lattice size in the X, the Y, and the Z direction. And is that showing you just what materials it's composed of, or is that showing you properties of the material and the crystals it forms?
That's a good question. So it's not going to show me. It's going to show me how the repetitions are. So in other ways, the rule of the land. So now I said that we define a rule of the land and try to create it, right? Using PLD. That was the whole purpose of PLD. But once we create it, we want to characterize it that we actually happen to have created that rule of the land. In other words, the symmetry, the square lattice, you remember? We want to check after a distance away, there is all the lattice, there is all the atoms we wanted to create on the horizontal direction. And in the vertical direction, there are all the in the horizontal direction along the B direction, B distance away, and in the vertical direction, all a distance away. That's what we want to verify, and that's what we verify using this four-circle diffractometer.
Okay, so this is just ensuring that you correctly made the material you set out to make.
Absolutely, and also like figuring out if you have an unknown material. Like for example, there are complicated materials where you cannot define the lattice spacing so easily, like in a direct way. Like for example, quasi crystals, where there is like some weird things happening. And I'll show you at the end of the day how weird things can come up. And like it's not very straightforward to say that, okay, we wanted to create this like that, and we hope to create that like, but it didn't. And there are many things happen. Anyways, I'm gonna show you our, if there is no other questions right now. Okay. So this is the four-circle diffractometer. And this is completely lead shielded because there is X-rays inside, but it's not running right now. So I'm gonna open it, and this is the four-circle diffractometer. You can find the resemblance with the slide image that I was showing. The X-rays come from that hole there. So this is like a copper X-ray generator. And the X-rays hit the sample which is usually housed here. And this can rotate like this along the arc. This is the chi motion. And moving this is the theta motion or omega motion from the slides. This is a separate arm, which is the detector. Like you can see, this is a different arm altogether. It can move independently. So omega, chi, and theta, all three are like you can move it and measure where the intensity goes after scattering. And once you map the whole K area, you kind of like once you map the whole angular area, you kind of know how it looks in reciprocal space. I'll show you how the look moves. So this is like the control panel for this thing, and let me see. These are usually very laggy. Look, this is one of the measurement that I took a few days ago. This tells a lot about the system. We have a substrate and the thin films. These are so the red thing is only a substrate where there is no thin film grown. The black curve is a substrate with thin film grown on it. So these humps there, these are the signatures of the thin film. Okay, do you have any questions? Oh, I guess it started to listen to me. So let's so this is how the whole thing moves. It's extremely accurate in moving. That's the one thing we need from this motion. So it's like 0.001 degrees it can take. So that's a whole lot of accuracy in when you are trying to figure out some complicated structures. So if there is no other question, yeah, right? Yes, that's a good question. When I need an extra example of a phi is imagine basically when I'm thinking in terms of domains. So for example, any sample that we have in single crystals. So okay, so what we have discussed so far is thin film materials, right? Which is like a slab on a substrate. But it can be a single crystal, which is grown in a different way, which is not using PLD, but there are like different procedures. And one can do a whole PhD on how to grow a single crystals. And the famous single crystal grower are very big guys in the field. But how to, so the single crystals, they have little domains. I need to explain things. So they have little domains. Now, little domains don't exactly follow the surface normal. So sometimes they are rotated like this, sometimes they are rotated like this, and things like that. So if you want to figure out if your sample needs a bit of, maybe your sample is a bit off in order to probe the exact dimension, HK dimension. So you kind of need to rotate the samples in a way, the exact domain where you're hitting with X-rays, that is required just to rotate the phi in that angle, basically search and then figure out if that is the phi, fix the phi, and do the rest of the things again. So in other words, in I'm close. By the way, I'm closing the for circle. If someone wants to see something else, or rather, otherwise I'm closing. Okay, so so yeah, basically, you can imagine to be like you have in a three-dimensional spherical coordinate system, you have you need three degrees of freedom: r, theta, and phi. Now, r is provided by the wavelength of the thing, or the theta to theta combination, whereas the phi and theta. So this is like a redundant degree of freedom, but everything can be accessed by 2 theta and phi, or omega and chi. So these are the circumstances
I think the audio on the mobile cut out.
Yeah. Third floor has a very bad internet connectivity. I'm sorry that you got to be entertained in a different way. Yeah, the question that I was referring to is question of if there how to use the phi motion. Is that if there is like domain distribution, and domains are like, so some of the domains are like this, say, let me use Tom's phone. So this is, some of the domains are like that, and some of the domains are like this. If you hit in this domain at certain phi angle, you're gonna get the data. But now suppose you did not, and you instead hit this domain, because they're so little, there is no way you know which domain you are hitting. Now you have to rotate the phi, to make them in line. So make this guy look like the guy which was previously, and then do the experiment. So it's a combination of searching. How many different ways you can search? If that explains anything. All right, so moving on. Is my screen shared? Maybe. Right. So phi becomes important in lattices with many domains. If there's like a domain orientation, so phi you can imagine to be the orientation. So A and B axis. So imagine you have a lattice where all of the A and B axes are like this. So this is a bit. So A is like this and B is like that, some things like that. And so now if you have A and B axis defined, you kind of have this, sorry. But if you have A and B axis rotated in a phi, you kind of had to adjust it when you do the experiment. That's where phi comes in. If that's, yeah. Okay, cool. Yes, I got it. Awesome. So yeah, now I'm gonna show. I'm coming back to this. Okay. So yeah,
Shormishta is here, who is the legendary PLD filmmaker. She went straight to making films. Anyways, yeah, so the whole thing is that there is like reciprocal space is in HKL, which is the integer units, after which you expect to see the periodicities in A and B star. No. You want to say hi? There are kids here. They're right here. Hi, this is Shormishta. She is the legendary thin film maker in our lab. Yeah, she makes amazing thin films. I just showed you one of the thin films. I showed that without the films, there is this substrate peak, the only one peak, but with films, there is this oscillations around that peak. So yeah, that's she. Okay, thank you. So yeah, this is the so this is a right example of a thin sample. So this is how in real space the sample looks like. This is like a black crystalline thing. Its surface is shiny, so it reflects off the light as you look at it, and it mimics like a metallic thing at room temperature. Like looks like a metallic thing, but it's actually way more complex than it. The lattice structure looks something like this, where there are layers. There is bismuth and oxygen layers. Oxygen are the little orange dots. Bismuth are the blue dots. And then there is this layer of strontium and oxygen. And then there is this extremely complex copper oxygen layer. There is another calcium layer, and the whole thing repeats, but in a mirror way. Now, this is a very complex material. It's kind of a material where what we study. We shine it with X-rays, exactly like that, in the 4-circle diffractometer. Vary our omega, vary our chi, vary to theta. Theoretically, the right-hand side is how the reciprocal space would look like. Every dot here represents every point here on the right-hand side is an intensity. The intensity, if it is like red, it's high intensity. If it's blue, it's low intensity. But every point here represents intensity. The blue patch here is where we take a reading. Now you see here, we are supposed to see that H is equal to 0, L is equal to 10, an intensity, H is equal to 0, and L is equal to 12, another intensity, H is equal to 2, and L is equal to 10, and a super bright intensity, and H is equal to 2, L is equal to 12, another intensity. So 4 intensity, what we expect to see, this blue patch. But this is what we see, this monstrosity. We see the 10 and 12 at H is equal to 2, H is equal to 0. Why this is, anyways, and we also see at H is equal to 2, the 10 and 12, but they are kind of smooshed. We see a new thing at H is equal to 2.4 or something, and L is equal to 10. And there are so many things other than that. So not only the symmetries dictate, there are many more things to it than what the symmetries and these are very complex materials. So the structures are not really straightforward. Any questions? I'll keep this up if that helps to bring up the question. This is what I do every day. Like I take samples. Is someone asking a question? Okay, so yeah, this is what I do every day. Like I take samples from Ishtadi or samples from Maya, who grows single crystals. I haven't touched a lot on single crystals because I don't have any understanding how to grow them. It's a very complex procedure. Maya knows best in our group. Alejandro knew. Alejandro, I'm gonna do the cartoon call at the end, but they are the masters of single crystal growth. Shomistadi and Dong, they know PLD system very well. And yeah, and there are different other ways to do like magnetic sputtering. That's another way to grow crystals, and so on. Like I think magnetic sputtering is for thin films, not for crystals. So yeah, if there is no other question, I will take this X-ray, shining X-ray smartly on a steroid. Like this is the most basic experiment that we can do, whatever we have shown. And this is the first step, and from here we start the complexity one by one, because the materials that we study, the materials that I'm showing you right now, is a high temperature superconducting material, which is the most elusive material that there ever was. For 35, I think it's 80. It was invented in 1985, and so like even after like 35 years, no one knows exactly what happens inside this material. Like, and it has developed physics way more than everybody thought it could. Like there is like all new theories and all new experiments are designed, all new data are collected just to explain a little bit, like even the thing at exactly one doping level or something like that. Like I can tell you, like last week I had been doing an experiment on cuprates for straight 7 days, and we got few data. The thing that we were not sure, well, first of all, when we saw a signal, we were like, yay, we got something and happy time. But then we realized that may not be a signal, and that may be a noise. And we analyzed it for rest of the days we had in the beam time, and we realized it's complete BS. And that's experiment for you. Like it's easy to fool yourself that you have come across something very important, but most of the time it is not. Any questions? If there is no question, I'll talk about how we can do it in a more complicated ways. So we can remember the picture, like this picture. We can do XRD in a way that there is like the X-ray only sees the Bi atoms, say, or X-ray only sees the calcium atoms, or the copper atoms only, or the oxygen atoms only. Or for example, we can do an experiment and like we can shine X-rays in a way it sees not only the copper atoms, but the p orbitals of copper atoms. So that is what we call resonant. So this is resonant X-ray diffraction we can do. We can do nano deflection, where the beam spot size becomes very small, like 30 nanometer small. So this is like 300 times the smallest lengths or 100 times the smallest length scale. So we are only focusing on 100 nano, like 100 unit cells at a time. We can do it in a coherent X-ray diffraction way. Now, coherent is like another whole beast there, because once when you can think of it as a 2D Fourier transform taken as a whole. So it's coherent X-ray diffraction is an interference experiment, like Michelson interferometer. X-ray photocorrelation spectroscopy is a coherent diffraction, but where you run a movie. So you take snapshots every time and correlate the snapshots with each other. We can do X-ray absorption spectroscopy. So these are all on the real space data, with some degrees on electronic characterization. But there are only electronic characterizations as well, which is like X-ray absorption spectroscopy or X-ray magnetic dichroism, photoelectron emission spectroscopy, RPIS. But these are all the facilities that we don't have in our lab. So how do we do it? So we grow samples, we grow single crystals or thin film. We then characterize them in-house. Like we characterize them using the XRD, X-ray diffraction unit that I showed you. We characterize them using the thermal transport. So we measure their resistance, we measure Hall transport, we measure magnetization with temperature. We can study now the reciprocal space, that is the structure of it with temperature. Then to do all those things in like steroid mode, we take them to like APS in Chicago, we take them to ALS in Berkeley, NSLS2 in Brookhaven, and SSRL in Stanford. So these are the all places where they have extraordinary experimental facilities. We also go to Canada. There's an Oxford beamline, German, yeah, around the world basically. There are fantastic beamlines where we use the synchrotron to do the experiment. What is a synchrotron? Synchrotron is a X-ray source which is extremely tuned to do some kind of experiments. So here there is like an electron source. The electron goes into a storage ring, stays there for some time. Then it's flown into another bigger storage ring where these red things are there. What are those red things? Red things are like bending magnets. Now when electron bends, it emits X-rays because it's going in a deceleration. And that X-ray is sampled along this tangent. And this feed into this experimental facility. And we sit here somewhere in these computers and do our do the experiments using those control panels. The things that we study in basic physics are like high temperature superconductors that I have shown an example of, quantum spin liquid candidates, quantum phase transitions. We study interfaces and 2D materials. We study interplay of symmetry and topology. We also study predictive assembly of nanoparticles. These are all the basic physics phenomena. Once we know something about the basic physics, we want to apply them. In application-oriented side, we apply it on spintromics. That's like the younger brother of like electronics. It's more cool, more gadgety, less energy hungry, more efficient, and all that. We are developing a brain using this new physics in quantum systems, neuromorphic computing, we call it, where our connections will behave as a brain, and like it will be the hardware side of artificial intelligence, or machine learning as we know it, and self-assembly of nanoparticles, which Dong is leading, where we are studying how the nanoparticles are self-assembled, so they can be functionalized. Say, for example, there are 5 nanoparticles, and that can behave like an angle or like a clamp or something like that. We can also we are developing new things with metal organic frameworks where we change a particle inside a virus and control the virus, and so that becomes a functionalized virus. So we just use it as a carrier. So we load it with something, some information to deliver it, or medicine to deliver it at a particular cell we want, and deliver it there. So that are other applied sides of it. And this is the curtain call. Yes, and we have our El Patron, Alex Frano, and Shomishta D you met. She is the leading in PLD. Ivan was there for XPCS and coherent studies. He was amazing, and he recently left like a few months ago. He is now in Germany and doing his second postdoc in Tübingen, University of Tübingen. Alejandro was amazing. He did his study in spin liquids and also some quantum phase transitions. And he is right now, he was here till last November. He went to MIT for his second postdoc. And Brandon and me are the senior most grad students in this loop, and we started our journey I think in 2018. Yeah, it's way back. Anyways, yeah, so we are studying quantum particles, quantum systems basically. Vishwajit is a shared graduate student with Fullerton group. He is studying spintronic systems. Elliot is also Vishwajit's cohort, and he is studying BO2 systems, which is another quantum system. Dong and Maya are the first year students. They have joined us this year, and Dong is studying strong interaction in classical regime like nanoparticles. Maya has studied quantum spin liquids with Alejandro, and she has amazing experiences with single crystal growth. Dong has amazing experiences with PLD growth. Evening was an undergraduate student with us. He just got an admission at Caltech, so he's gonna leave us down the line. Brandon is an undergraduate student currently, and he is studying the as far as I remember, he is studying also the quantum systems. Also, we have a new undergrad students. I couldn't get, I have met her, and I couldn't get a hold of her because all of this was like extremely in a hurry. Her name is Reno Salmons. She's in the audience.
Yeah, hi.
Hi, Reno. Yeah, I love. I don't know what you are exactly working on, and so sorry. It came like after we made all the slides like last night. Everything happens last night.
Oh, please, I'm not offended at all. Like, I totally understand. It's still a little up in the air exactly what I'm doing, but I can email you about it some other time.
Of course. I'd love to hear about these. Okay, so any questions? Or any comments, like anything at all, like how to do an experiment or how it feels like?
I have a general question. So our club has several undergraduate physics students, and do you have any advice for those undergrad students who want to get into research?
I mean, in terms of like how to get prepared for the research?
I guess the whole procedure, like contacting professors, if none of the professors are responding, what sorts of things you can do on your own to prepare. Like maybe if you've done any individual projects just on your own for fun, what sorts of things?
Yeah, so what I found that most interesting ways to get a professor involved is every one of us is extremely curious, right? So if you can talk in their language, that's the most helpful thing. So you got to talk in their language. So how to talk in their language? It's extremely difficult to break like through the published articles because most of us are not prepared for that. At like even I am not prepared. Like I read a article. It takes me about a month to understand the bare minimum what the article wants to say. So so first of all, be very like attend the colloquiums. Colloquiums are a great place to start. See where your interests lie. Then find articles like in Physics Today or Scientific American. Physics Today articles usually have like a good references. So read those articles, then follow those references. Wikipedia page of that usually has a bit of references, but most of the references will not come handy because they're like a bit far. There are very good actually YouTube lectures now that you can follow. Sometimes like Veritasium that has a very good like way of explaining things. They have amazing 3 blue 1 brown. That's another channel that I find handy. And so these are the next level that and there you'll find another new term and just googling that term and like following the thread. It's like a rabbit hole. You after some time of chasing around, you kind of see the lay of the land and try to project whatever you see onto what you are learning. If you cannot, just go and ask those questions to your professor who is teaching you. That's the best way I can offer. And then in terms of like if a professor is not responding, I guess just move on to the next.
Cool, thank you. And then I had another one. What sorts of classes did you take that prepared you for this sort of research? Like what sorts of specialized classes?
I would say Physics 152A and Physics 152B, the condensed matter physics one. Yeah. Yeah, that's what I did. I was an undergrad at UCSD last year, and that's the class that I took. Yeah.
Awesome, thank you.
Yeah, it's not very straightforward, and I would say like from my personal experience, research is it depends on if you are curious enough. It's the main ingredient that will drive you through the day. There is everything else will try to stop you. So just get your curiosity extremely high and you'll find a way. Any other questions and in terms of like our works or anything that maybe we have connected to you what you are studying and you have a question from there as well, maybe we can try that. not, then I'll hand over to Zach, I guess.
Sounds good. I'm not seeing anyone chirp up either. But thank you, Ruoff and Dong, so much for showing us a little bit about what research at UCSD looks like, and just giving us more aspects of science to be confused about than we had at the start of the day. I appreciate that. We'll share the link to your lab in case any students want to contact you or Dr. Frano to learn a little bit more. And again, we appreciate you and good luck with your studies.
Feel free to come, like, knocking my door. Like, I am at 3531, and I can explain physics with social distancing nowadays. So. Bye.
We will take you up on that. Thank you.
Thank you.
Thank you.
Thank you.
Yes, log